Hello everyone, this is Team 3. For our project, we decided to do a hose reel redesign. My name is Noor Hadid. Please meet my teammates.
My name's Arushi.
I'm Yoan.
And I'm Nick.
Hose reels are simple devices with the primary function of conveniently storing a fluid-carrying hose for easy access at any time. These hoses are intended to be installed in workplaces where fluids frequently need to be delivered to specific locations by means of a hose. Next slide, please.
Okay. This is the exploded view of the hose reel. The reel can be separated into three main parts: the frame, the spring drive system, and the reel. We are treating the spring drive as a black box as we will not be modifying it.
Our primary customer base are any form of automotive shops. Air tools are the most common form of tools mechanics use when dealing with fasteners to replace components. Thus, that makes the hose reel a very convenient choice for them. Our secondary customer base are horticulturists, which are professional gardeners, and since the majority of elders choose to pick up gardening, having our redesigned, easily maneuverable hose reel will make gardening significantly easier.
Our main function would be to store this tube, and it is divided into subfunctions relating to housing that tube and other functions that the hose reel should contain.
This is our function component mapping matrix. As we can see in the chart, there are a few components that are critical to performing many of the functions of the device and therefore represent potential points of failure which can be redesigned. The components that we have selected as modular and changeable between the two customer categories each fulfill only their own respective functions. Our quad chart classification breaks down the parts on the hose reel by manufacturing cost and functional importance. Parts with high functional importance but also high cost are to be considered for redesign. In our case, these are the tube reel, spring hub, reel spindle, and spring drive. Unfortunately, redesigning the spring drive is beyond the scope of this project, so it will be maintained as a cost. The parts listed as low functional importance, that is roller supports, roller holders, and roller holder plate, are to be eliminated with the next design iteration or brought to a higher functional value.
Our product family design is as follows. There are different wall mounts for different purposes. Horticulturists would prefer a garden hose, so a mount would be portable, and an auto shop would prefer a mount in an auto shop with an air hose. For the next slide here, there are different subcomponents and subassemblies in which they're each divided into.
This is our CAD for the primary and secondary customers. As you can see, the secondary customer just has an easy carry handle. On the next slide, we can see the color coordination showing us where each piece is installed with respect to the primary and secondary customer. As it is seen, it is very easy to customize. With respect to the fast diagram, the functions that are not shared across our customer layouts are the following: provide stability, facilitate portability, accommodate tube, retract tube. We achieve this by changing the wall mount to an easy carry handle to facilitate portability and to change the tube stopper size to accommodate the tube's girth.
This is our operation time for our original design. We identified that fasteners 3 and 4, which attach the support, as well as 17 and 18, which attach the mount, could be optimized in our redesign.
The part that we decided to redesign is the roller support and the bridge support, as these parts are both of high functional importance according to our quad chart, which by consolidating we reduce the total amount of critical failure points. It also spreads the cost of the bridge support, which is a high cost part according to the quad chart, to the roller support, which is a low cost part, ultimately decreasing manufacturing costs. The consolidation complies with the DfM guideline that if two parts do not move relative to each other, do not need to be of different materials, and do not need to be separated to allow assembly, they can be merged. This redesign minimally impacts the part's function, but it may make it slightly weaker than if it is two separate parts. The module part that we decided to optimize, the two steps identified two slides prior, is the mount. This redesign eliminates 4 fasteners and is focused on the mount, our module part. This is a functionally important part as identified in the quad chart since it provides stability to the full assembly. The DFA redesign on it is meant to optimize the duration of time that it takes to install the part. Using snap fits instead of fasteners may increase manufacturing costs and reduce the part strength. However, the time savings of using snap fits is significant and takes precedence.
As can be seen by the grayed out portions, we eliminate the nut and screw set number 1 and number 3, as well as the roller support. By doing so, our time went from 5.5 minutes to a measly 3 minutes.
In automated assembly, there's a little bit of redundancy for parts, as can be seen with the figure for minimum parts. Since many of these parts have a similar function, we can calculate the cost be $9.06 for all the parts in this subassembly. This assembly was specifically chosen because there were many small parts and they were all consolidated in a very small place.
The subassembly we selected, as mentioned previously, contains several small parts with, nonetheless, with a high functional importance, such as the roller support and the tube rollers. According to the FCMM, these parts perform important functions, such as preventing kinks in the tube and allowing it to retract and protract smoothly. The redesign follows several important DFA considerations for automated assemblies, such as the fact that parts must be easily orientable, should be able to maintain their orientation as they're assembled, and must easily be oriented within a vibration table.
So the impact of redesigning this tube roller and combining its function with the roller holder is that there allows there to be one part instead of two for the same exact function. Since there are less of these redundant parts, we can tell uh, that the cost is also significantly reduced. As you can see, we are around $2.50 less than we were for designed for automated assembly before. This makes a large impact since the functional importance and, as shown in our quad chart, can combine these two parts together.
Moving on to process selection for our manual DFA part. According to the
Can you hear me
FCMM, one of the
breathing? So
critical
we're gonna
functions of
restart
the
this
roller
run.
support, which is present within this part, is to allow the tube rollers to rotate smoothly in order to allow them to smoothen the motion of the tube, and in addition to retracting and allowing it to protract. Therefore, the critical dimensions are the 63.18 millimeter and 37.78 millimeter clearances between the shaped roller holders, and that puts the tolerance at plus or minus is half a millimeter because the CAD contains some additional allowances in between to account for any errors in manufacturing. The second part that we are looking at for process selection is the injection molded tube rollers. This redesigned tube roller facilitates the motion of the tube, and according to FCMM, it must allow it to, again, smoothly protract and retract the tube, meaning that the critical dimension is the 62 millimeter length, which sits between the aforementioned roller holder mounts. If it is too long, it will get caught in the support structure and will get stuck, which will inhibit the retracting motion.
Based on the redesign of the bridge support, we can say that the tolerances are not as necessary since there are very large clearances for the parts around the bridge support. As well as that, there were two possible processes that would work for this bridge support, which would be machining and sheet forming. However, uh, after an overall analysis, machining would be way too expensive, so sheet forming would be the better choice. For the tube roller, basically, this part also had the possibility to be either machined or injection molded. However, machining again has a very high cost, so therefore we are sticking to injection molding. The critical dimension is the length of the large roller. If it is way too large, it will not fit in the bridge support.
This is our cost analysis for our DFA redesign. There are 4 steps, and our total cost comes out to $5.40 per part at a quantity of 200,000 a year and a 1-year payback period.
This is our cost estimation using hubs.com. As we can see, the price comes out to be significantly greater. This is most likely due to the fact that we're extrapolating the model beyond its useful limits.
This is our injection molding process, which ends up to be a price of 44 cents, taking into consideration material costs, machine operating costs, and mold costs.
This is a screenshot of DfM Pro's suggestions on the sheet metal part in terms of DfM. A screenshot of the injection molded part from DfM Pro. This is a screenshot of our DfM redesign for the sheet metal part. This follows design DSFM 6 to avoid round corners, DSFM 8 to widen the holes past depending on the gauge, and DSFM 9 to provide bend relief when required, as highlighted in the photo. This is our injection molded part DFM redesign. It follows DFIM 1, which suggests minimizing wall thickness in injection molded parts, DFIM 2, which means to keep the wall thickness uniform, and DFIM 4, avoid sharp corners.
This is our cost analysis on our DFM redesign. There are 4 steps, and our total cost comes out to $5.34 per part at a quantity of 200,000 and a 1-year payback period. We chose to use an automated press for these steps as it was cheaper than the manual sheet metal working cost.
This is the hubs.com estimation for the post DFM sheet metal part. As we can see, the cost is still actually higher than it was before, and this is again most likely due to the fact that the model is being extrapolated beyond useful limits.
The next part that we have is the roller. This piece is a very simple piece. It is injected molded with no side pulls, internal cores, lifters, or unscrewing devices, thus making it a very cheap price to manufacture. Using the material of ABS, we were able to produce this part at 16 cents per part.
For our product service systems, pre-purchase we plan to offer multiple models with and without a hose attached, and post-purchase we plan to offer machine shops and other people using it for air compression or for compressed air, both compressed air generators as well as storage systems. And for our seasonal gardeners, we plan to offer a region-dependent rental system.
Overall, the team worked very, very hard. Through doing DFA, the team has managed to drastically improve the assembly time by over 40% and reduce the parts by
Overall,
35%.
the team works very, very hard.
We have also managed to improve the time to manufacture the project, and there is less material usage as well. Upon reflection, we noticed that the original CAD was not very accurate to the real product, which we fixed, and we redesigned many of the smaller parts into pieces that are combined. In retrospect, our design may be challenging to an unskilled machinist due to the complexity, and we will want to redesign the CAD as a very first step before starting to do our work. Thank you for listening to our presentation. Okay, that was 12 minutes and 20 seconds.